What if everything you know has a hidden twin, a secret counterpart, identical yet unseen, lurking just beyond the edges of our reality? Picture this: every atom, every star, every galaxy you've ever marveled at might have a shadowy double, a mirror image existing in a parallel realm. This isn't science fiction. It's one of the most tantalizing mysteries in modern physics, the enigma of mirror matter. Scientists call it the hidden twin to everything we know, a ghostly duplicate of ordinary matter that could be woven into the very fabric of the cosmos. And if it's real, it could rewrite our understanding of the universe itself. Think about the world around you, the chair you're sitting on, the device in your hand, even the air you breathe. Now imagine an invisible version of all of it, made of particles that are nearly identical to the ones we're familiar with, but just out of reach. These mirror particles wouldn't interact with light the way ordinary matter does, which means they'd be completely invisible to our eyes, our telescopes, even our most advanced detectors. They could be passing through you right now, and you'd never know. That's the eerie beauty of mirror matter. It's everywhere and nowhere all at once, a cosmic phantom hiding in plain sight. But why should we care about something we can't even see? Because this elusive twin could hold the answers to some of the universe's biggest puzzles. From the missing mass that keeps galaxies from flying apart to the strange asymmetry between matter and antimatter, mirror matter might be the missing piece we've been searching for. And the hunt for it is already underway, with physicists around the world designing ingenious experiments to catch even the faintest whisper of its existence. So buckle up, because today we're diving into one of the most mind-bending frontiers of science, where the ordinary meets the extraordinary, and the universe might just be far stranger than we ever imagined. To grasp mirror matter, let's start with a simple but mind-bending idea. What if every particle in the universe had a twin with one crucial difference? Not an evil twin, not an antimatter twin, but something subtler, a mirror image version of itself. Picture your hands. They're nearly identical, but try stacking them palm to palm. They don't line up perfectly. That's chirality, a fancy way of saying handedness. Ordinary matter, like the stuff that makes up planets and people, has a specific chirality, a kind of cosmic left or right-handedness. Mirror matter flips that. It's like the universe's way of creating a reflection, a shadow version of reality where everything is subtly inverted. This isn't just a fun thought experiment, it's rooted in serious physics. The idea first gained traction when scientists noticed something odd about the fundamental forces governing particles. Some equations in particle physics work too symmetrically, as if nature left room for a hidden counterpart. Enter mirror matter, a theoretical form of stuff that behaves almost exactly like ordinary matter, but with flipped chirality. Because of that twist, it barely interacts with the forces we're familiar with, especially light. That's why you might hear it called shadow matter or even Alice matter, a nod to Through the Looking Glass, where everything exists in a twisted reflection of the real world. But here's where it gets wild. If mirror matter exists, it doesn't just sit silently in some parallel dimension. It could be right here, woven into the fabric of our universe. Think of it like a ghostly echo passing through walls, planets, even you, without leaving a trace. No light bounces off it, no electricity conducts through it, and yet it might make up a significant chunk of the cosmos. Some scientists suspect it could even explain the invisible glue holding galaxies together, dark matter. Could mirror matter be the missing piece we've been hunting for all along? The answer might be hiding in plain sight, just mirrored. The story of mirror matter begins with a shocking discovery that turned physics upside down, literally. In the 1950s, two young physicists, Tsung-Dao Lee and Chen-Ning Yong, stumbled upon something strange. They noticed that nature seemed to have a favorite direction, a kind of cosmic bias. At the time, everyone assumed the laws of physics were perfectly symmetrical, that the universe didn't care if you looked at it normally or in a mirror. Flip an experiment left to right and the results should stay the same. That principle was called parity symmetry, and it was considered unshakable. But Li and Yang had a bold thought: what if it wasn't? Their hunch led to one of the most dramatic moments in modern science. Another physicist, Qin Wu, designed an experiment to test their idea using radioactive cobalt atoms. If parity symmetry held, the atoms should decay symmetrically, spraying electrons equally in all directions. But when Wu flipped the experiment's orientation, the electrons didn't play fair, they had a clear favorite direction. It was as if the universe had a secret left-handedness, a preference that shattered the illusion of perfect symmetry. The discovery earned Li and Yang a Nobel Prize and opened the door to a bizarre possibility. If the universe wasn't symmetrical, maybe it used to be. Maybe there was a hidden counterpart, a mirror version of reality that balanced the scales. That's where the idea of mirror matter was born. If nature had a bias, perhaps it was because we were only seeing half the picture. Think of it like a pair of gloves, left and right. If you only ever saw left-handed gloves, you might assume gloves only come in one form. But the full set exists even if the right-handed ones are hidden. Some physicists began to wonder, could there be a mirror sector of particles identical to ours but with flipped chirality, quietly correcting the cosmic imbalance? Over the decades, this speculative idea grew legs. Researchers realized that if mirror matter existed, it wouldn't just be a philosophical curiosity, it would have real, measurable consequences. For one, it could explain why the universe seems so lopsided when it comes to matter and antimatter. After the Big Bang, equal amounts should have been created, canceling each other out and leaving nothing behind. But somehow matter won. Mirror matter could be the invisible player that tipped the scales. Even more compelling, it might be the elusive dark matter that astronomers have been chasing for decades, the unseen mass that holds galaxies together. Today, the search for mirror matter blends cutting-edge theory with bold experiments. Underground detectors wait for phantom collisions, while particle smashers hunt for anomalies that could betray the presence of a hidden twin universe. The legacy of Li and Yang's parity violation lives on, not just as a historical footnote, but as a clue to one of the deepest mysteries in physics. Because if mirror matter is real, it wouldn't just change textbooks, it would mean we've been sharing our universe with a ghostly double all along. If you've heard of antimatter, you might think mirror matter sounds similar, but these two cosmic doppelgangers couldn't be more different. Antimatter is like the rebellious twin of ordinary matter, carrying the opposite electric charge. When an electron meets its antimatter counterpart, a positron, they annihilate each other in a burst of energy. It's a dramatic, explosive relationship. Mirror matter, on the other hand, is far more subtle. Instead of opposing charges, it flips something far more elusive, chirality or handedness. Imagine trying to shake hands with your reflection. Your palms wouldn't quite meet. That's the essence of mirror matter. It's not about annihilation, it's about inversion, a quiet mirroring of the universe's underlying structure. While antimatter has been produced in labs and even used in medical imaging, mirror matter remains purely theoretical for now. The key difference lies in how they interact with the forces we know. Antimatter still plays by the same electromagnetic rules as ordinary matter, just with opposite charges. But mirror matter, it might barely interact with electromagnetism at all. Light would pass right through it, making it completely invisible to our detectors. That's why some scientists suspect it could be hiding in plain sight, woven into the fabric of space itself. Here's where things get even stranger. Antimatter is rare in our universe, a cosmic imbalance that's puzzled physicists for decades. Mirror matter, if it exists, might not be rare at all. In fact, it could be everywhere, outnumbering ordinary matter by a huge margin. That's why some researchers think it's a prime candidate for dark matter, the mysterious substance holding galaxies together. While antimatter annihilates on contact with matter, mirror matter could simply drift right through it untouched. The two might even be connected in unexpected ways. Some theories suggest that mirror matter could help explain why the universe favors matter over antimatter in the first place. If a mirror sector exists, it might have its own version of antimatter too, creating a hidden cosmic balance we've yet to uncover. So while antimatter steals the spotlight with its explosive energy, mirror matter operates in the shadows, quiet, elusive, and potentially far more transformative to our understanding of reality. Chirality might sound like an abstract concept, but it's the key to unlocking why mirror matter could be so elusive. At its core, chirality describes a fundamental handedness in particles, a directional preference baked into the fabric of reality. Imagine a spinning top. If it rotates clockwise, no amount of flipping or twisting will make it spin counterclockwise unless you change its fundamental motion. Particles behave similarly, with their spin and momentum locked into a specific orientation. Ordinary matter, like the electrons and quarks that build our world, leans heavily toward one chiral preference, left-handed for most particles, right-handed for others. But what if there's a shadow version of these particles, identical in every way except their chirality? That's the heart of mirror matter, a universe where every particle's spin is flipped like a reflection in a cosmic mirror. This flipped chirality isn't just a trivial detail, it's the reason mirror matter might be practically invisible to us. In particle physics, interactions are governed by forces like electromagnetism and the weak nuclear force, and these forces care about chirality. Ordinary matter interacts strongly because its particles match the chiral preferences of these forces, but mirror matter with its opposite-handedness would be out of sync. It's like trying to fit a left-handed glove onto a right hand. The pieces don't connect. For mirror particles, this mismatch means they'd barely feel electromagnetism at all. Light would pass right through them, and ordinary matter would offer no resistance, as if they were phantoms drifting through solid walls. Here's where it gets even more intriguing. The weak nuclear force, responsible for radioactive decay, is notoriously picky about chirality. It interacts almost exclusively with left-handed particles. If mirror matter is right-handed, it would ignore this force entirely. That's why experiments designed to catch dark matter, like sensitive underground detectors, might be missing mirror matter altogether. They're built to look for particles that interact weakly, but mirror particles could interact so feebly that they're practically ghosts. Even neutrinos, the famously elusive particles that barely interact with anything, would seem downright chatty compared to their mirror counterparts. Yet chirality isn't just a barrier, it's also a clue. If mirror matter exists, its inverted symmetry could explain one of the universe's great imbalances, why there's so much more matter than antimatter. In the early cosmos, a slight preference for left-handed particles might have tilted the scales, allowing matter to dominate. Mirror matter, with its opposite chirality, could have played by different rules, quietly balancing the equation in a way we're only beginning to glimpse. It's a tantalizing thought. The universe's hidden twin might not just be hiding in the shadows, it could be the reason we exist at all, and that's the beauty of the chirality problem. It's not just a quirk of particle physics, it's a doorway to a deeper layer of reality. Every time scientists study the subtle asymmetries in particle decays or design experiments to probe the limits of known forces, they're searching for whispers of this mirrored world. Because if chirality is the universe's way of keeping secrets, mirror matter might be its most carefully guarded one. Right now, as you watch this, entire galaxies are spinning at speeds that defy the laws of physics, at least the laws as we understand them. Stars on the outer edges of spiral galaxies whip around so fast that they should fling themselves into the void, yet something invisible holds them in place. Astronomers call this mysterious force dark matter, but for decades, its true nature has remained one of science's greatest enigmas. Here's where mirror matter steps in, not just as a theoretical curiosity, but as a potential solution to this cosmic puzzle. Imagine a galaxy like our Milky Way. Based on the visible matter, stars, gas, dust, its gravity shouldn't be strong enough to keep those outer stars from flying away. Yet they stay put, orbiting as if gripped by an unseen hand. Scientists estimate that dark matter makes up about 85% of the universe's total mass, outweighing ordinary matter by nearly 6-to-1. But if dark matter is everywhere, why can't we detect it directly? That's where mirror matter offers a compelling answer. Unlike other dark matter candidates, which rely on hypothetical particles dreamed up to fit equations, mirror matter emerges naturally from an elegant symmetry in physics. The idea that every particle we know has a hidden twin with flipped chirality. If mirror matter exists, it wouldn't just be sprinkled through space, it could form vast, invisible structures mirroring our own cosmic landscape. Picture a duplicate Milky Way made entirely of mirror particles, overlapping our own but drifting through it like a ghost. Its gravity would tug on ordinary stars and galaxies, explaining why we observe the effects of dark matter without seeing its source. Even more intriguing, mirror matter wouldn't clump together the way ordinary matter does. Without the electromagnetic force to make it stick, it would spread into diffuse halos around galaxies, perfectly matching the gravitational fingerprints astronomers have traced for decades. The evidence goes beyond rotation curves. Take galaxy clusters where the gravitational pull is so strong that it bends light itself, a phenomenon called gravitational lensing. The amount of bending we observe requires far more mass than visible matter can account for, again, pointing to dark matter. Mirror matter's gravitational influence would explain these cosmic mirages without invoking entirely new physics. Some theories even suggest that mirror matter could seed the formation of galaxies in the early universe, providing the gravitational scaffolding for ordinary matter to cling to as stars and planets coalesced. But the most tantalizing clue might come from the cosmic microwave background, the afterglow of the Big Bang. Tiny temperature fluctuations in this ancient light reveal how matter was distributed in the infant universe, and the patterns align eerily well with models that include mirror matter. Ordinary matter alone can't explain the delicate balance of those fluctuations, but add a mirror sector, and suddenly the math clicks into place. Of course, not everyone is convinced. Critics argue that mirror matter, while elegant, is still speculative, a fix that hasn't yet been proven. After all, if it's truly invisible to light and barely interacts with ordinary matter, how do we find it? That's where experiments like neutron lifetime measurements come in. Neutrons decay at a predictable rate unless something interferes. Some researchers suspect that a fraction of neutrons might be transforming into mirror neutrons, vanishing from our detectors and hinting at a hidden particle sector. Other experiments search for faint gravitational anomalies or subtle imbalances in cosmic particle collisions, any of which could betray the presence of mirror matter's ghostly touch. What's remarkable is how neatly mirror matter ties together so many cosmic loose ends. It doesn't just explain dark matter's gravitational effects, it offers a unified picture of the universe's hidden architecture. If confirmed, it would mean we're living in a dual cosmos, where every star, every planet, every speck of dust has a silent counterpart. The galaxies we admire through telescopes would be joined by shadow galaxies, the universe's hidden twin finally stepping into the light. Until then, the hunt continues, with physicists peeling back the layers of reality to ask, are we alone in our own universe, or has the answer been staring back at us all along, mirrored? The hunt for mirror matter isn't just happening in theory, it's playing out in labs around the world, where scientists are pushing the limits of technology to catch even the faintest trace of this elusive cosmic twin. One of the most promising avenues, neutron oscillation experiments. Picture a lone neutron, a fundamental building block of atoms sitting in a detector. Normally, it decays into a proton, an electron, and a neutrino in about 15 minutes. But what if some neutrons aren't decaying at all? What if they're vanishing into thin air, morphing into their mirror counterparts right under our noses? That's the wild idea behind neutron oscillation, a process where neutrons flip between ordinary and mirror states, disappearing from our observable universe like cosmic sleight of hand. Experiments like those at the Institut Langevin in France or the Los Alamos Neutron Science Center in the U.S. have spent years meticulously tracking neutrons, measuring their lifetimes with exquisite precision. Any discrepancy, any missing neutrons that can't be accounted for by ordinary decay, could hint at mirror matter slipping through the cracks. So far, the results are tantalizing but inconclusive. Some studies show slight anomalies in neutron behavior, small gaps that mirror matter could theoretically fill. But pinning it down requires ruling out every other possibility, a painstaking process that's like searching for a whisper in a hurricane. Meanwhile, other experiments are probing the boundaries of particle physics for mirror matter's fingerprints. Precision measurements of atomic behavior, for example, look for tiny deviations in how electrons orbit nuclei. If mirror particles lurk nearby, their gravitational pull, however faint, could nudge ordinary atoms in ways that defy standard predictions. Projects like the Stanford-based Action Dark Matter experiment, originally designed to hunt for other dark matter candidates, have retooled their detectors to scan for mirror matter's subtle gravitational effects. Even the slightest wiggle in a carefully calibrated magnetic field or an unexpected blip in a particle collision could be the clue that cracks the case. Then there's the cosmic angle. Astronomers aren't just waiting for mirror matter to show up in labs, they're scouring the skies for its gravitational echoes. When neutron stars collide or black holes merge, the ripples in spacetime they create could carry hints of mirror matter's influence. Advanced detectors like LIGO and Virgo, which listen for these gravitational waves, might one day pick up anomalies that point to hidden mass interacting in ways we can't yet explain. Even the way galaxies cluster on vast scales could betray the presence of mirror structures, invisible threads woven through the cosmic web. What makes this search so thrilling is its sheer creativity. Without direct interaction, mirror matter forces scientists to think sideways, designing experiments that don't just look for particles but for the absence of them, for the shadows they cast rather than the substance. It's a bit like trying to find a burglar who leaves no fingerprints, no footprints, just an open window and a nagging sense that something's off. Every null result, every dead end, tightens the constraints, narrowing the possibilities until perhaps mirror matter has nowhere left to hide. The stakes couldn't be higher. If even one of these experiments catches a whiff of mirror matter, it wouldn't just confirm a wild theory, it would rewrite the rules of reality. Suddenly, dark matter wouldn't be an abstract placeholder in equations. It would have a face, a structure, a mirror image logic we could begin to decode. And that's the beauty of this hunt. Whether mirror matter is found or finally ruled out, the quest itself is stretching the boundaries of human ingenuity, proving once again that the universe's greatest secrets are often hidden in plain sight, just waiting for us to look at them the right way. The idea of a mirror universe isn't just about hidden particles, it's about an entire reality operating alongside our own. A cosmos where every star, every planet, and maybe even every living thing has a counterpart we can't see or touch. This isn't just science fiction. Some physicists seriously entertain the possibility that mirror matter isn't just scattered bits of unseen stuff, but structured into a full-fledged parallel universe, complete with its own laws and history. Imagine two sheets of paper stacked together, one transparent, the other opaque. We live on the opaque sheet, unaware of the other unless we find a way to peek through. What would this mirror universe look like? If it obeys the same basic laws as ours, it might have its own atoms, molecules, and even galaxies, all built from mirror particles with flipped chirality. Stars that could burn with nuclear fusion just like ours, but their light, if you could call it, that wouldn't be visible to our eyes or telescopes. Civilizations might rise and fall in that shadow realm, never knowing we exist, while their gravity subtly tugs on our galaxies from the shadows. The concept stretches beyond dark matter. It suggests a full cosmic duplicate, echoing our universe in every way except one: its fundamental handedness. The roots of this idea trace back to symmetry in physics. Our universe seems asymmetrical at a fundamental level. Parity violation shows nature prefers left-handed particles. But what if that's only half the story? Theoretical models propose that the Big Bang didn't just create our universe but spawned a pair, with the mirror universe balancing the scales. In this view, the apparent asymmetry we observe is just an illusion, a side effect of being trapped on one side of a cosmic mirror. The full picture would restore perfect symmetry, with both universes together obeying laws far more elegant than those we see. Life in a mirror universe raises even wilder questions. Could mirror DNA exist? Could consciousness arise in beings made of particles that barely interact with ours? Some theories suggest mirror matter might have its own forces, analogues to electromagnetism or the strong nuclear force, but entirely separate from ours. Chemical reactions there would follow familiar patterns, but the ingredients would be invisible to our detectors. If life did emerge, it would evolve in a world where light, as we know it, doesn't exist. Their eyes might detect some other force, their hands built from atoms that pass through ours like ghosts. Not all scientists are convinced, of course. Critics argue that a mirror universe is untestable by definition. If it doesn't interact with us, how could we ever prove it's there? But supporters counter with subtle clues. If mirror matter clusters into mirror galaxies, their collective gravity could leave faint imprints on the cosmic microwave background, or distort the paths of distant starlight in ways ordinary dark matter can't explain. Others hunt for rare instances where mirror particles might leak into our world, like neutrons oscillating between states or unexplained energy losses in particle collisions. The most tantalizing possibility, that the mirror universe isn't just a passive shadow but actively shapes our reality. Some models suggest the two universes could have collided in the distant past, leaving scars in the distribution of galaxies or the afterglow of the Big Bang. Others propose that mirror matter played a role in the universe's initial inflation, its presence tweaking the expansion rate in ways that left traces we might yet discover. Whether the mirror universe is real or not, the hypothesis forces us to confront how little we truly understand about reality. For all our telescopes and particle smashers, we might be missing half the cosmos, not because it's too far away, but because it's written in a language of symmetry we're only beginning to decipher. Every time a physicist measures a neutron's lifetime or maps the gravitational tugs of distant galaxies, they're not just probing our universe, they're knocking on the door of another, asking if anyone's there to answer back. If mirror matter exists in the quantities physicists suspect, it wouldn't just lurk in the background, it would have shaped the cosmos from its very first moments. Picture the Big Bang not as a single explosive birth, but as a symphony of two intertwined universes, one ordinary, one mirrored, unfolding in perfect counterpoint. The energy released in that primordial instant would have been split between them, with mirror particles flooding into their own shadow realm while our familiar matter coalesced into atoms and light. This division could explain one of cosmology's deepest puzzles, why the universe appears so finely tuned. The cosmological constants, numbers governing the strength of gravity, the speed of light, even the expansion rate of space, seem improbably precise for life to exist. But if a mirror universe balances ours, those fine-tuned values might not be accidents at all. They could be the inevitable result of symmetry, a cosmic seesaw where our universe's constants are mirrored and moderated by its hidden twin. Take cosmic inflation, the theory that the universe underwent an exponential growth spurt in its first fraction of a second. If mirror matter was present during this epoch, its gravitational pushback might have acted like a hidden regulator, preventing runaway expansion from tearing spacetime apart. Some models suggest that mirror particles could have formed invisible seeds for structure in the early universe, their gravity gently nudging ordinary matter into the filaments and voids we see in today's cosmic web. Without this influence, galaxies might never have clumped together so efficiently. It's a breathtaking thought. The vast, glittering superclusters we map with telescopes could trace the outlines of something far stranger, an echo of mirror matter's ghostly scaffolding. Even the universe's lopsided matter-antimatter imbalance might find an answer in this mirrored cosmology. Moments after the Big Bang, particle collisions should have produced equal amounts of matter and antimatter, which would have annihilated each other, leaving behind a sterile sea of radiation. Yet somehow, 1 in every billion matter particles survived. Mirror matter offers an elegant solution. What if antimatter wasn't destroyed but transformed? Through a process called leptogenesis, particles might have oscillated between ordinary and mirror states, with a slight preference for matter settling into our universe while antimatter drained into the mirror realm. The result, our matter-dominated cosmos, isn't an anomaly, it's half of a hidden equilibrium, balanced by a mirror universe where antimatter reigns supreme. On the largest scales, mirror matter's influence could rewrite our understanding of dark energy, the mysterious force accelerating the universe's expansion. If mirror particles permeate space, their unique properties might alter how gravity behaves across cosmic distances, mimicking the effects of dark energy without requiring new physics. Alternatively, the gravitational tug-of-war between our universe and its mirror counterpart could create subtle ripples in spacetime, warping the paths of galaxies in ways that standard models fail to predict. Already, astronomers have spotted anomalies in the Hubble constant, the rate of cosmic expansion, that vary depending on where and how it's measured. Could this Hubble tension hint at mirror matter's gravitational fingerprints? The most radical possibility, that mirror matter didn't just influence the early universe, it is the early universe. Some theories propose that what we call dark matter is actually the relic of a mirror Big Bang, a separate creation event that unfolded alongside ours. In this scenario, the two universes would share spacetime but remain forever out of phase, like parallel train tracks that never meet. Collisions between them would be vanishingly rare, but their combined gravity would weave the fabric of reality itself. If true, it would mean we've been misreading the cosmos for decades, mistaking half the story for the whole. Every time astronomers peer deeper into the void, they uncover new mysteries, galaxies rotating too fast, gravitational lenses bending light too sharply, voids in the cosmic web stretching too wide. Mirror matter offers a unifying framework for these puzzles, not by inventing new particles or forces, but by revealing a symmetry hidden in plain sight. The universe, it seems, has always been whispering its secrets. We're just learning to listen in stereo. Imagine a star just like our sun. Same size, same fiery core, same nuclear reactions blazing at its heart, but made entirely of mirror matter. To our telescopes, it would be utterly invisible, a phantom presence in the cosmos. Yet its gravity would still bend the paths of nearby stars, tugging on them like an unseen puppeteer. Astronomers have actually detected such anomalies, stars mysteriously wobbling as if orbited by massive companions we can't see. We call these hidden objects dark stars, and while black holes or rogue planets could explain some, mirror stars fit the puzzle just as neatly. Picture a binary system where one star shines bright while its twin, a mirror star, dances alongside it in perfect gravitational sync, leaving no trace but its pull. Now scale that up. Entire galaxies could harbor mirror counterparts, shadowy duplicates of their spiral arms and glowing cores, overlapping the visible universe like a cosmic double exposure. Planets might orbit these mirror stars, cloaked in the same eerie invisibility. If mirror matter interacts with its own version of electromagnetism, these worlds could have mirror atmospheres, mirror oceans, even mirror geology. A mirror Earth might boast towering mountains and deep valleys, its surface sculpted by mirror plate tectonics or eroded by mirror rivers, all completely imperceptible to us except through the faintest gravitational whispers. The real tantalizing question, could mirror life exist? If mirror chemistry operates like ours, with mirror atoms bonding into mirror molecules, the ingredients for biology might be there. Enzymes, proteins, even DNA-like structures could evolve in this hidden realm, following the same rules of complexity but built from flipped particles. A mirror microbe wouldn't just be alien, it would be untouchable, thriving in an ecosystem that never interacts with ours. Think of it like two radio stations broadcasting on different frequencies. Both carry music, but neither hears the other. Critics argue that without efficient energy transfer like starlight warming a planet, mirror life seems unlikely. But mirror stars might emit their own form of radiation, invisible to us but potent in their realm. Photosynthesis could work the same way, with mirror plants absorbing mirror photons. Predators might hunt, cells might divide, civilizations might rise, all in a parallel reality that shares our space-time but not our senses. Here's the twist: even if mirror life thrives, we'd have no way to confirm it. Traditional astrobiology searches for biosignatures like oxygen or methane in atmospheres. Mirror biosignatures would be equally hidden, their chemical fingerprints written in ink we can't read. The only clue might come from gravity, perhaps an unnaturally smooth orbit suggesting artificial megastructures, or a planet whose mass doesn't match its size, hinting at hollow spaces within. The sheer scale of this possibility rewrites the Drake equation, the famous formula estimating intelligent civilizations in our galaxy. If mirror matter is abundant, the number of potential life-bearing worlds could double, with entire mirror civilizations unknowingly sharing our cosmic neighborhood. They might gaze at their own mirror night sky, puzzling over the same gravitational anomalies we attribute to dark matter, never suspecting they're the hidden half of a universe they'll never see. Until we detect definitive proof, a neutron flipping states, a gravity anomaly with no other explanation, mirror stars and planets remain speculative. But that's the thrill of frontier science. Sometimes the wildest ideas push us to look harder, dig deeper, and question what we think we know. After all, the universe has surprised us before. Who's to say it isn't hiding its greatest marvels not in distant galaxies, but right beside us, just beyond the mirror? At the heart of every galaxy lurks one of the universe's most enigmatic objects, a black hole, a region of space-time so warped that not even light can escape its grip. But what if these cosmic monsters have hidden counterparts, shadows of themselves made not of ordinary matter, but mirror matter? The idea isn't as far-fetched as it sounds. Black holes, by their very nature, are defined by gravity, and gravity doesn't care about chirality. A mirror matter black hole would still curve space-time just like its ordinary sibling, but the way it forms and evolves could be radically different, leaving behind clues that might finally reveal mirror matter's existence. Take stellar collapse, the dramatic death of a massive star that births most black holes we know. In our universe, a star runs out of fuel, implodes under its own weight, and leaves behind a singularity shrouded by an event horizon. But a star made of mirror matter would follow the same script with one critical twist. Its particles wouldn't emit the light or radiation we associate with supernova. A mirror star's death throes would be silent, invisible, detectable only by the gravitational ripples it sends through space-time. When it finally collapses, the resulting black hole would be indistinguishable from an ordinary one, at least at first glance. Here's where things get fascinating. While black holes famously have no hair, a catchy way of saying they're defined only by mass, spin, and charge, mirror matter could give them a secret wardrobe. Theoretical models suggest that a black hole formed from mirror matter might interact differently with its surroundings, especially if some mirror particles linger nearby. Ordinary black holes accrete visible matter, heating it into glowing disks of plasma. A mirror black hole, though, would feast on mirror matter, creating an invisible accretion disk that emits no light but still tugs on nearby stars with its gravity. Astronomers might spot these phantom feasts by tracking stars that orbit nothing their paths, hinting at an unseen mass devouring an unseen meal. Even more bizarre. Mirror black holes could warp space-time in ways that defy expectations. If mirror matter responds to its own version of forces like mirror electromagnetism, a black hole infused with it might exhibit subtle distortions in how it bends light passing by. Gravitational lensing, the phenomenon where black holes magnify distant galaxies like cosmic telescopes, could reveal anomalies. A mirror black hole's lensing effect might be slightly off, warping background starlight in patterns that don't match predictions based on visible mass alone. These tiny discrepancies, like a fingerprint smudged at the edges, could betray the presence of mirror matter lurking within. Then there's Hawking radiation, the faint glow of particles that quantum mechanics predicts black holes should emit as they evaporate. For ordinary black holes, this radiation is a mix of photons and other known particles. But a mirror black hole, it might spew mirror particles invisible to us, yet still carrying away energy. Over eons, this could lead to a mirror black hole decaying at a different rate than its ordinary counterpart. If we found ancient black holes suspiciously smaller or larger than their ages suggest, mirror matter might be the culprit behind the mismatch. The most tantalizing possibility involves black hole mergers. When two black holes spiral into each other, they send gravitational waves rippling across the cosmos. But if one of those black holes is made of mirror matter, the collision could leave an odd signature in the waves, an extra wobble in the signal, or a frequency shift that doesn't align with standard models. Advanced detectors like LIGO and Virgo are already picking up these space-time tremors from ordinary mergers. One day, they might catch an anomaly that points to something far stranger, a mirror black hole crashing through the cosmic veil. At the edge of theory lies an even wilder idea. Mirror matter could alter a black hole's very fabric. Some models suggest that mirror particles might form a kind of quantum atmosphere around the event horizon, subtly changing how infalling matter behaves. Others speculate that mirror black holes could tunnel through extra dimensions, creating bridges or wormholes to their mirrored counterparts. These hypotheses stretch the limits of known physics, but they underscore a thrilling truth. If mirror matter clumps into black holes, it wouldn't just hide in the shadows. It would rewrite the rules of the darkest objects in the universe. For now, the hunt for mirror black holes remains a game of indirect clues and patient observation. But every anomaly in gravitational wave data, every unexplained lensing distortion, every star orbiting empty space could be a breadcrumb leading to a revelation that black holes, those perfect voids in spacetime, aren't so simple after all. They might be cosmic chameleons concealing a mirrored reality within their inky depths. And if we're clever enough to decode their secrets, we might finally glimpse the universe's hidden twin, not in the stars but in the darkness between them. Quantum mechanics already paints reality as a strange and shimmering tapestry, a world where particles can be in two places at once, where observation changes outcomes, and where entanglement links objects across vast distances instantaneously. Now imagine threading mirror matter into that tapestry. The result isn't just complexity, it's a quantum revolution waiting to happen. At the heart of this idea lies quantum field theory, the framework that describes particles as ripples in invisible fields permeating the universe. In this picture, every particle we know, electrons, quarks, photons, is an excitation of its corresponding field. But what if there's a second set of fields, perfectly symmetrical to ours yet invisible? That's the radical proposition of mirror matter in quantum physics, a shadowy duplicate of every field and particle, vibrating just out of phase with our own. Start with the photon, the particle of light. In our universe, photons mediate electromagnetism, zipping between charged particles to create the forces that hold atoms together. A mirror photon would do the same, but only for mirror matter. It would be oblivious to ordinary charged particles, rendering it completely undetectable by our instruments. Yet it could still bind mirror atoms into molecules, power mirror stars, even create mirror lightning in mirror storms. The catch, without any interaction with our electromagnetic field, mirror light would pass through us like we're made of glass. The night sky might be ablaze with mirror constellations, and we'd never know. Electrons, the workhorses of chemistry and electricity, take on an eerie duality in this mirror world. A mirror electron would have the same mass and spin as its ordinary counterpart but opposite chirality, like a left-handed glove swapped for a right-handed one. In quantum terms, this means it would couple only to mirror photons and mirror weak nuclear forces, making it impervious to the forces that shape our everyday world. Yet if a mirror electron drifted through a lab, its presence might subtly distort the quantum vacuum, the seething sea of virtual particles that fills empty space. Experiments hunting for vacuum fluctuations have already glimpsed anomalies that standard physics can't explain. Could these be whispers of mirror electrons brushing against the edges of our reality? The weak nuclear force responsible for radioactive decay adds another layer of intrigue. Ordinary weak interactions violate parity symmetry. They prefer left-handed particles. Mirror weak forces, if they exist, would flip this preference, interacting exclusively with right-handed mirror particles. This split could explain why mirror matter stays so stubbornly hidden. Our detectors are tuned to left-handed signals, deaf to the right-handed murmurs of the mirror sector. But occasionally, quantum mechanics might allow particles to tunnel between worlds. Neutrons, for example, could oscillate into mirror neutrons, vanishing from our universe in a puff of quantum weirdness. Experiments monitoring neutron lifetimes have spotted puzzling deficits gaps mirror matter could neatly fill. Then there's the Higgs field, the cosmic molasses that gives particles their mass. If mirror matter exists, it might have its own mirror Higgs, a hidden counterpart to the field discovered at the Large Hadron Collider in 2012. This twin Higgs could endow mirror particles with masses eerily similar to ours or wildly different. Some theories suggest mirror protons might outweigh ours by orders of magnitude, making mirror stars denser and hotter than anything we've observed. Others propose that the mirror Higgs interacts feebly with ours, creating a fragile bridge between sectors. If colliders like the LHC found the Higgs behaving oddly, decaying at unexpected rates or producing imbalanced energies, it could hint at this hidden connection. Quantum entanglement, arguably the spookiest phenomenon in physics, takes on new dimensions with mirror matter. Normally, entangled particles influence each other instantly, no matter the distance. But what if entanglement could cross the mirror boundary? A mirror electron paired with an ordinary one could act as the ultimate quantum telegraph, transmitting information between realms without any measurable signal in between. While this sounds like science fiction, some models of quantum gravity suggest spacetime itself might be built from entangled connections. Mirror matter could be weaving that fabric in ways we're only beginning to imagine. The implications stretch beyond theory. If mirror particles interact via their own version of quantum fields, they might form exotic states of matter unlike anything we've seen. Mirror superfluids with zero viscosity, mirror superconductors that defy the laws of resistance, even mirror quantum computers processing information in parallel to ours, all could exist in the shadows. Some physicists speculate that dark matter's odd behavior, like its reluctance to clump on small scales, might reflect the quantum properties of mirror particles. Their wave-like nature could prevent them from collapsing into dense objects, spreading instead into diffuse halos around galaxies. Critics argue that adding mirror matter to quantum field theory complicates an already counterintuitive framework. But supporters counter that nature adores symmetry and mirror matter restores a balance broken by the parity violation we observe. It's not just about inventing new particles, it's about uncovering a deeper elegance in the universe's design. Every unexplained quantum anomaly, every mismatch between theory and experiment could be a breadcrumb leading to this hidden twin. The next time you hear about a perplexing quantum result, a particle behaving unpredictably, a force not quite matching calculations, consider this. We might not just be missing pieces of the puzzle. We might be missing half the board, and somewhere beyond the veil of detection, mirror particles could be dancing to the same quantum rhythms as ours, their steps perfectly synced yet forever unseen. The universe, it seems, is far stranger than we thought, and far more symmetrical than we dared to hope. Across the cosmos, astronomers keep stumbling upon phenomena that defy explanation, gaps in our understanding so glaring they hint at something fundamental we're missing. Take galaxy rotation curves for starters. When scientists measure how fast stars orbit the center of a spiral galaxy, the outer stars move far too quickly for the visible matter alone to hold them in place. According to Newton's laws, those stars should be flung into the void like marbles off a spinning plate. Yet something invisible grips them, anchoring them with an unshakable gravitational hold. Dark matter is the go-to explanation, but here's the twist. Mirror matter fits the data just as neatly. If galaxies are embedded in vast halos of mirror particles, their collective gravity would tug on visible stars exactly as observed, no exotic particles required. Then there's the bizarre case of the bullet cluster, one of the most striking pieces of evidence for dark matter. This cosmic collision between two galaxy clusters sent hot gas clouds smashing together, slowing down due to friction, while the cluster's gravity, traced by lensing effects, kept racing ahead. The interpretation: most of the mass wasn't in the gas but in something invisible passing through the collision unscathed. Mirror matter could be that ghostly component. Unlike dark matter candidates that rely on hypothetical weakly interacting particles, mirror matter naturally avoids electromagnetic interactions, making it the ultimate bulletproof material in such cosmic smash-ups. But the anomalies don't stop there. Some galaxies appear to lack the gravitational scaffolding we'd expect from their visible structure. Ultra-diffuse galaxies, for instance, are enormous yet so faint they're barely detectable. Their stars are spread so thin that conventional models suggest they should have disintegrated long ago, yet they persist, seemingly held together by unseen mass. Mirror matter could explain this too. If these galaxies formed in regions rich with mirror particles, their diffuse stars might simply trace the edges of an invisible mirror matter core, like foam on an ocean wave. Even more puzzling are galaxies that rotate as if they're too smooth, lacking the clumpy dark matter concentrations predicted by simulations. These missing dark matter galaxies shouldn't exist under standard models, yet they do. Mirror matter offers an elegant fix. If ordinary and mirror matter segregate over time due to their differing interactions, some galaxies could end up mirror-dominated while others become mirror-starved, creating the observed inconsistencies. It's a cosmic sorting mechanism that no other dark matter theory can replicate. Gravitational lensing adds another layer of mystery. When astronomers map the distortion of background light around massive galaxy clusters, they often find concentrations of mass that don't align with visible matter. Some lenses produce multiple, oddly spaced images of the same distant object, a sign of hidden mass warping spacetime in ways we can't account for. Mirror matter's gravitational pull would sculpt these light-bending patterns perfectly, without the need for ad hoc adjustments to dark matter models. In one striking example, the galaxy cluster Abell 521 exhibits lensing so extreme that its visible mass accounts for less than 10% of the effect. Mirror matter could be the silent architect behind this cosmic hall of mirrors. Then there's the Hubble tension, the growing discrepancy in measurements of the universe's expansion rate. Different techniques keep yielding conflicting results, suggesting our cosmological models might be incomplete. If mirror matter interacts weakly with ordinary matter but still contributes to the overall mass-energy budget, it could subtly alter the expansion history, reconciling these conflicting measurements without invoking new physics. These aren't isolated puzzles, they're pieces of a larger pattern, gaps where mirror matter slots in with uncanny precision. From phantom galaxies to gravitational mirages, the cosmos seems to be whispering the same secret. What if the missing piece wasn't missing at all, just mirrored? Every unexplained wobble, every warped beam of light could be a footprint of this hidden twin, quietly shaping the universe from the shadows. As telescopes peer deeper and simulations grow sharper, the answer may not lie in inventing new physics, but in recognizing the reflection we've overlooked all along. Neutron stars are among the most extreme objects in the universe, cosmic cinders so dense that a single teaspoon of their material would weigh billions of tons on Earth. These collapsed stellar cores pack the mass of a sun into a sphere no wider than a city, creating gravity fierce enough to bend light into loops. But what if these ultra-dense relics harbor a secret? Hidden deep within their cores, beyond the crush of ordinary neutrons, could lurk something even stranger, a heart of mirror matter, twisting their behavior in ways that betray its presence. Picture a neutron star moments after its birth, when the dying star's core collapses under its own gravity. At these insane pressures, atomic nuclei dissolve into a sea of neutrons, with occasional protons and electrons squeezed into the mix. But if mirror matter exists, some of those neutrons might not stay ordinary for long. Quantum mechanics allows for the possibility of neutron oscillation, a fleeting transformation where a neutron flips into its mirror counterpart. Over time, these flipped neutrons could accumulate, sinking toward the star's center under their own immense gravity, forming a mirror matter core. The result: a neutron star with a hidden twin at its heart, an invisible nucleus wrapped in a shell of familiar matter. This ghostly core wouldn't just sit idly by. Mirror matter responds to gravity just like ordinary matter, but without the electromagnetic interactions that create friction or radiation. A mirror core could rotate independently of the neutron star's outer layers, like a gyroscope spinning inside a second gyroscope. Over millennia, this mismatch might slow the star's spin in unexpected ways, leaving telltale gaps between predicted and observed rotation rates. Some pulsars neutron stars that beam radiation like cosmic lighthouses exhibit glitches, sudden speed-ups in their rotation that defy conventional models. Could these be the echoes of a mirror core slipping, lurching, or even cracking under the strain? Then there's the puzzle of neutron star cooling. Young neutron stars should blaze with heat from their violent birth, gradually radiating energy away as they age. Yet some neutron stars cool far faster than theories predict, as if their thermal energy is draining into an invisible sink. A mirror matter core could explain this. If heat from ordinary matter seeps across the boundary into the mirror sector carried by rare interactions or quantum tunneling, it would vanish from our view, cooling the star faster than expected. Astronomers tracking the temperature of neutron stars have noted anomalies that align eerily with this idea, as if these cosmic furnaces are leaking energy into another realm. Even more striking are the hints from gravitational waves. When neutron stars collide, the ripples they send through space-time carry fingerprints of their internal structure. In 2017, the LIGO and Virgo observatories detected waves from such a merger, revealing a neutron star with a surprisingly low maximum mass. Some physicists argue this could point to a softening of the star's core, precisely what might happen if mirror matter lurked within, altering how the star resists collapse. Future gravitational wave detections could look for similar anomalies, searching for the subtle distortions that betray a mirror matter heart. Perhaps the most tantalizing clue comes from quark matter, a hypothetical state where neutrons break down into their constituent quarks under extreme pressure. Some theories suggest that mirror matter could catalyze this breakdown, transforming a neutron star's core into a hybrid of ordinary and mirror quarks. The result, a star with bizarre properties, like an ultra-dense shell surrounding a strangely squishy interior. Observations of neutron stars with inexplicably low surface gravity or odd vibration patterns might one day reveal this duality, offering smoking gun evidence for mirror matter's role. The hunt for these cosmic chimeras is already underway. Telescopes like NICER, which maps the surface hotspots of neutron stars, are scrutinizing their sizes and temperatures for discrepancies. Other teams are simulating how mirror cores would affect starquakes' violent crust fractures that send shudders through a neutron star's magnetic field. Even the way neutron stars wobble as they spin, a phenomenon called precession, could hold clues. A mirror core would shift the star's balance like a hidden weight, tweaking its wobble in ways detectable by sensitive instruments. Neutron stars have long been laboratories for the universe's most extreme physics. Now, they might also be windows into a mirrored reality. Every anomaly in their spin, their heat, their quakes, or their collisions could be a message written in gravity and quantum whispers, hinting that the universe's most crushing objects are hiding something unimaginable. Not just remnants of dead stars, but portals to a shadow cosmos waiting to be decoded. In the universe's earliest moments, long before stars or galaxies even existed, the cosmos was a seething cauldron of energy and particles, a place where the very laws of physics were being forged. Amid that primordial chaos, mirror matter could have played a role so profound it shaped everything that followed. Picture the first minutes after the Big Bang, a time known as Big Bang nucleosynthesis, when the universe was still young enough to fit inside the orbit of Mars, yet hot enough to fuse the first atomic nuclei. Ordinary matter, protons and neutrons, collided fiercely, forming deuterium, helium, and traces of lithium. But if mirror matter was present, it would have danced to its own nuclear tune, creating a shadow version of these processes. The result, a hidden reservoir of mirror deuterium, mirror helium, even mirror hydrogen, all invisible to our telescopes but potentially outnumbering the elements we see today. The cosmic microwave background, that faint afterglow of the Big Bang etched across the sky, holds even deeper clues. This ancient light carries imprints of density fluctuations, tiny ripples in the early universe that eventually grew into galaxies and clusters. If mirror matter existed back then, its gravity would have subtly warped these ripples, leaving a distinct signature in the CMB's temperature patterns. Some models suggest that mirror particles could have acted as invisible scaffolding, gently tugging ordinary matter into the filamentary structures we now observe. The Planck satellite's precise maps of the CMB reveal slight anomalies, areas where the fluctuations don't quite match predictions. Could these mismatches be whispers of mirror matter's gravitational handiwork woven into the universe's blueprint? One of the most puzzling features of the early universe is its staggering smoothness. No matter which direction we look, the CMB's temperature is nearly identical across billions of light years, a fact that defies explanation unless the infant cosmos underwent a period of exponential expansion called inflation. But inflation's mechanism remains mysterious. Mirror matter offers a tantalizing twist. If the inflaton field, the energy driver behind inflation, had a mirror counterpart, the two sectors could have interacted in ways that fine-tuned the expansion. Picture two balloons inflating side by side, one visible, one invisible, their growth linked by a hidden symmetry. This coupling might explain why our universe's initial conditions were so finely balanced, avoiding the chaotic unevenness that pure chance would predict. Then there's the mystery of lithium. According to Big Bang nucleosynthesis models, the universe should contain about 3 times more lithium-7 than we actually observe. Astronomers call this the cosmological lithium problem, and it stumped scientists for decades. Mirror matter could provide an elegant solution. If some of the neutrons involved in those early nuclear reactions oscillated into mirror neutrons, they'd vanish from our observable universe, reducing the final lithium yield. Experiments trying to replicate these primordial conditions have noted slight discrepancies in reaction rates, gaps that mirror matter could neatly fill. But perhaps the most dramatic implication lies in the universe's very geometry. The total density of matter and energy determines whether spacetime is flat, curved, or closed. Observations confirm a flat universe to extraordinary precision, but ordinary matter alone can't account for it. Dark energy and dark matter make up the difference, or so we thought. If mirror matter contributes significantly to the cosmic density budget, it could alter our understanding of the universe's fundamental shape. Some theories even suggest that mirror matter's gravity might mimic the effects of dark energy, accelerating the expansion of space not through some mysterious repulsive force, but through the subtle interplay of 2 parallel sectors tugging on spacetime from opposite sides. The early universe wasn't just a simpler time, it was a laboratory for physics we're only beginning to grasp. Every anomaly in the CMB, every mismatch in nucleosynthesis, every unexplained smoothness or shortage could be a breadcrumb leading back to mirror matter's hidden influence. As cosmologists refine their models and next-generation telescopes probe deeper into the cosmic dawn, the answers may not lie in inventing new particles or forces, but in recognizing the reflection that's been there all along, a mirror universe, its fingerprints faint but indelible, waiting to be decoded from the oldest light in existence. Detecting mirror matter might be one of the most frustrating scientific challenges imaginable, like trying to catch smoke with your bare hands. Only the smoke doesn't even brush against your skin as it passes through. The problem boils down to one unavoidable fact. Mirror matter doesn't play by the same rules as ordinary matter. While we're used to particles that interact through electromagnetism, emitting light, bouncing off surfaces, or creating detectable electric fields, mirror particles ignore these forces entirely. They're cosmic phantoms drifting through walls, planets, and even our most sensitive detectors without leaving a trace. Take something as basic as light. Our entire understanding of the universe is built on it. Telescopes capture starlight, microscopes illuminate cells, even our eyes rely on photons hitting retinas. But mirror matter doesn't interact with photons. A mirror planet could be right in front of us, and our telescopes would see straight through it. Traditional astronomy is blind to this shadow realm, forcing scientists to get creative. Instead of looking for light, they're hunting for subtler clues, like gravitational tugs on visible stars or anomalies in the rotation of galaxies. It's like trying to map a room by feeling the breeze from an open window. You know something's there, but you can't see it or touch it. Then there's the challenge of particle detectors. Most are designed to catch interactions via electromagnetism or the weak nuclear force. When a neutrino, for example, zips through a detector, there's a tiny chance it'll bump into an atomic nucleus, releasing a flash of light or a burst of charge. But mirror matter doesn't even do that. With flipped chirality, mirror particles would sail past ordinary atoms without a whisper, making even the most sensitive underground labs, like those hunting dark matter, effectively useless unless they're reconfigured to catch something entirely different. One of the few potential handholds is gravity. Since mirror matter still has mass, its gravitational influence could betray its presence. Experiments like LIGO and Virgo, which detect ripples in spacetime from colliding black holes, might one day spot anomalies hinting at mirror objects. But gravity is an incredibly weak force. It takes something as massive as a planet or star to create detectable effects. A single mirror particle's gravitational pull would be so faint it'd drown in background noise. Scientists need vast amounts of mirror matter clustered together to even have a shot at measuring its pull, and even then, it's easy to mistake for ordinary dark matter. Another avenue is neutron oscillation, the idea that neutrons might occasionally flip into mirror neutrons. If true, this would mean neutrons in sensitive experiments could vanish without decaying, leaving behind an energy deficit. Teams have searched for this at facilities like the European Spallation Source, monitoring neutrons with extreme precision. But these experiments operate on knife-edge sensitivity. Even the slightest interference from cosmic rays or background radiation can muddy the results. And even if a neutron does disappear, proving it became a mirror neutron, rather than decaying via some unknown ordinary process, requires ruling out every other possibility, a painstaking task. Then there's the thermal angle. If mirror matter exists, it might occasionally bump into ordinary matter through ultra-rare, non-electromagnetic interactions. Some theorists suggest that these collisions could transfer tiny amounts of heat, causing unexplained temperature shifts in carefully isolated systems. Experiments like the cryogenic dark matter search have looked for similar effects, but again, distinguishing mirror matter from other exotic particles is like picking out a single voice in a roaring stadium. The sheer elusiveness of mirror matter forces physicists to think like detectives solving a case with no fingerprints, no witnesses, and a suspect that might not even be in the same dimension. Every experiment is a long shot, every potential signal buried under layers of cosmic static. But here's the kicker, even null results matter. Every failed attempt to detect mirror matter tightens the constraints, narrowing the possibilities until perhaps the only explanation left is the one that rewrites the textbooks. This isn't just a technical challenge, it's a philosophical one. How do you search for something that defies the very tools we use to explore reality? The hunt for mirror matter isn't just about finding new particles. It's about testing the limits of science itself, pushing our methods to their breaking point in pursuit of a universe that might be far richer and far stranger than we ever dreamed. And if that search teaches us one thing, it's that absence of evidence isn't evidence of absence sometimes. The most profound truths are the ones hiding in the gaps. The Standard Model of particle physics is one of humanity's crowning intellectual achievements, a meticulously tested framework that classifies every known particle and force, from the humble electron to the elusive Higgs boson. But for all its predictive power, the Standard Model has glaring gaps. It can't explain dark matter, the matter-antimatter asymmetry, or why gravity refuses to play nice with quantum mechanics. Now imagine throwing mirror matter into the mix. Suddenly, the model doesn't just have gaps, it might need a whole new wing. Take the concept of chirality, the handedness of particles that determines how they interact with the weak nuclear force. In the Standard Model, left-handed particles like electrons and neutrinos engage with the weak force, while right-handed versions don't, or at least not in the same way. This lopsidedness, called parity violation, was a shock when first discovered, but mirror matter proposes an elegant fix. What if right-handed particles do interact, just with a hidden mirror version of the weak force? This would restore symmetry at a fundamental level, implying the Standard Model is only half the story. Instead of a universe that favors left-handedness, we'd have a balanced cosmos where every particle has a mirrored partner, each obeying identical rules but in their own separate sectors. Then there's the Higgs mechanism, the process that gives particles mass. In the Standard Model, the Higgs field permeates space, and particles acquire mass by interacting with it. But if mirror matter exists, it would need its own Higgs field, a mirror Higgs, to give mirror particles their heft. Some theories suggest these Higgs fields could interact weakly, creating a fragile bridge between ordinary and mirror matter. Experiments at the Large Hadron Collider have already spotted slight anomalies in how the Higgs boson decays, tiny deviations from standard model predictions. Could these discrepancies be hints of mirror-Higgs interactions whispering from the other side of reality? Neutrinos add another twist. These ghostly particles barely interact with anything, oscillating between flavors as they travel. The standard model can't explain why they're so absurdly lightweight compared to other particles, a puzzle known as the neutrino mass problem. Mirror matter offers a compelling solution. What if neutrinos are so light because their mass is tied to mirror particles? In some models, neutrino oscillations aren't just between flavors but between ordinary and mirror states. This would mean every neutrino we detect is, at times, slipping into a mirror version of itself, an idea that would upend our understanding of these already mysterious particles. The most radical challenge mirror matter poses to the standard model, gravity. In the standard model, gravity isn't even a proper force, just a curvature of spacetime described by Einstein's general relativity. But if mirror matter exists, it would gravitate just like ordinary matter, meaning both sectors must share spacetime. This forces physicists to confront a question the standard model sidesteps. How do quantum fields and gravity really fit together? Some theories propose that mirror matter could act as a kind of dark glue, subtly modifying gravity on cosmic scales in ways that mimic dark energy or resolve inconsistencies in quantum gravity models. Critics argue that tacking on mirror matter makes particle physics needlessly complex, a fix that feels more like doubling the universe than explaining it. But supporters counter that nature often favors symmetry, from snowflakes to galaxy spirals. The standard model's asymmetries might not be flaws but clues, pointing to a grander design we've yet to uncover. Every time a particle collision defies expectations or a neutrino behaves oddly, it could be a nudge toward this hidden twin. The stakes couldn't be higher. If mirror matter is real, the standard model wouldn't be wrong, just incomplete, like a map missing an entire continent. Unifying it with mirror particles would require new mathematics, new experiments, perhaps even new laws of physics. But that's the thrill of the hunt. Whether mirror matter ultimately joins the standard model or falls to more elegant theories, its mere possibility stretches our imagination, proving that even our best science is still a work in progress, and the universe has plenty more surprises in store. What if we're not alone in the universe, but the evidence is literally right in front of us, just invisible? The possibility of mirror matter doesn't just reshape physics, it cracks open existential questions that make alternate dimensions or alien life seem almost mundane. Consider this: if mirror particles can form mirror atoms, which assemble into mirror planets orbiting mirror stars, could they also assemble into mirror trees, mirror oceans, mirror mines? The chilling answer is that we'd have no way to know. A mirror civilization could thrive alongside ours for millennia, building mirror cities and mirror technologies, warring or creating art or pondering our existence, all without leaving a trace in our observable reality. Their light wouldn't reach our eyes, their radio signals wouldn't crackle in our antennas. Even if their entire world ended in a mirror supernova, we'd detect nothing but the faintest gravitational ripple, indistinguishable from ordinary cosmic noise. The problem isn't just detection, it's definition. What even is life in a mirror universe? On Earth, life requires chemistry, molecules interacting via electromagnetism to replicate, metabolize, adapt. Mirror life would follow the same blueprint but with mirror chemistry. Mirror DNA could encode genetic instructions. Mirror neurons might fire with mirror neurotransmitters. But here's the twist: without shared forces, their biology would be as unreachable to us as a shadow is to a hand. You couldn't touch a mirror microbe, let alone communicate with a mirror scientist. Their entire ecosystem would operate like a parallel operating system, processing the same universe in a language we can't access. This raises an eerie corollary. If mirror life exists, we might be their dark matter. Just as we search for invisible mass holding galaxies together, mirror astronomers could be theorizing about strange gravitational anomalies, unknowingly measuring our planet's pull. Their textbooks might depict us as mysterious particles that clump around stars but refuse to interact. The irony is delicious. Two civilizations, mutually undetectable, each convinced the other is the universe's missing puzzle piece. Some philosophers argue this thought experiment reveals a flaw in our concepts of reality. We assume that to be real, something must be measurable, but mirror matter forces us to confront the limits of that assumption. If an entire civilization thrives unseen, does that make it less real, or does it expose how narrow our tools for defining reality truly are? The ancient question: if a tree falls in the forest and no one hears it, does it make a sound? Takes on new dimensions when the forest itself is made of shadow. Then there's the Fermi paradox, the puzzling absence of evidence for extraterrestrial civilizations. One proposed solution is that advanced societies eventually go dark, transitioning into forms we can't perceive. But what if they didn't choose invisibility? What if they were mirror beings all along, thriving in plain sight yet forever beyond our reach? The cosmos might teem with life, just rotated. A 90-degree turn in some abstract dimension, and suddenly their bustling metropolises flicker into view. The most profound implication isn't about finding mirror life, it's about redefining solitude. For centuries, humans have wondered if we're alone in the universe. But mirror matter suggests a far stranger possibility. We might be surrounded by neighbors we'll never meet, separated not by distance but by the very laws of physics. The universe could be a hall of mirrors, each reflection a self-contained reality, eternally close yet impossibly far. And if that's true, the greatest discovery ahead might not be contact, but the humbling realization that some doors, no matter how hard we knock, were never meant to open. Science fiction has always been a playground for the wildest ideas in physics, and mirror matter is no exception. Long before physicists coined the term, storytellers were dreaming up parallel worlds and shadow dimensions, uncanny reflections of our own reality where everything is just slightly off. Take Star Trek's mirror universe, a twisted version of the Federation where characters sport sinister goatees and loyalty is measured in betrayal. While the show never spells out the science behind it, the concept lines up eerily well with mirror matter theory. A realm where familiar faces act unpredictably, where light bends wrong, where the rules themselves feel inverted. That's not just campy space opera, it's a pop culture prophecy of what mirror matter might look like if it formed entire civilizations. Then there's Stranger Things, where the upside down lurks just beyond the veil, a decaying replica of Hawkins with its own toxic atmosphere and monster-filled shadows. The show's creators drew inspiration from real-world theories of alternate dimensions, but the parallels to mirror matter are striking. A world that mirrors ours yet operates by different physical laws. Check objects and people slipping between realms under rare, unstable conditions. That's almost textbook neutron oscillation. Even the eerie, void scenes in Doctor Strange, where reality fractures into infinite reflections, tap into the same fascination with symmetrical yet inaccessible realms. But sci-fi doesn't just borrow from physics, it often anticipates it. Philip K. Dick's The Man in the High Castle envisioned a world where history split into divergent timelines, while Fringe explored a parallel Earth where subtle differences snowballed into dystopia. These stories grapple with the same question physicists ask. If a mirror universe exists, how would its history diverge from ours? A single quantum fluctuation, a mirror star burning slightly longer, a mirror planet forming in a different orbit could cascade into a reality unrecognizable to us. Even horror gets in on the act. Annihilation, with its shimmering zone of genetic chaos, feels like a nightmare version of mirror matter's implications. If mirror particles could occasionally leak into our world, what would happen to biology? Would cells mutate? Would consciousness fracture? The film's alien landscape, where DNA recombines in impossible ways, plays like a cautionary tale about tampering with forces we don't understand. Gaming worlds lean into mirror matter's creep factor too. In Control, the oldest house shifts dimensions, its hallways rearranging like a Rubik's Cube of reality. The game's lore even name-drops mirror analogs, entities that exist in overlapping spaces. Sound familiar? It's a near-perfect metaphor for how mirror galaxies might coexist with ours, gravitational ghosts haunting the cosmic architecture. What's fascinating is how these fictional takes often stumble onto truths before science catches up. Star Trek's transporters, once pure fantasy, now echo quantum teleportation experiments. Stranger Things' sensory deprivation tanks, not far off from isolation chambers used to study consciousness. Mirror matter could follow the same path, from sci-fi trope to scientific frontier. After all, the line between speculative fiction and cutting-edge theory has always been thin. When Arthur C. Clarke wrote about geostationary satellites in 1945, they were fantasy. 20 years later, they were reality. Perhaps the most poignant exploration comes from Solaris, where an alien ocean manifests physical copies of a protagonist's buried memories. The story isn't about mirror matter, but its themes of realities that reflect our deepest selves yet remain fundamentally alien resonate with the idea of a hidden twin universe. If mirror life exists, would it reflect our triumphs and failures, or would it be so foreign that even gravity can't bridge the gap? These stories do more than entertain. They prime us to think in multiples, to question whether our universe is the only version of itself. Every time a character steps through a looking glass or battles their doppelganger, they're rehearsing a possibility physics is only now taking seriously. And who knows, the next great leap in understanding mirror matter might not come from a lab, but from a line of dialogue in a cult classic, or a throwaway detail in a graphic novel, proof that sometimes truth doesn't just imitate art. It waits for art to imagine it first. For all its elegance, mirror matter theory faces fierce skepticism from scientists who argue it's more mathematical fantasy than testable reality. The biggest hurdle: no one's ever directly detected it. Every other particle in the standard model leaves traces, tracks in cloud chambers, flashes in detectors, patterns in accelerators. Mirror matter, by definition, dodges these entirely. Critics point out that proposing an entire shadow universe of particles that can't interact with ours borders on unfalsifiable, a clever idea that can't be proven wrong, which in science often means it can't be proven right. If a theory doesn't make predictions we can verify, how is it different from speculation? Then there's Occam's razor, the principle that the simplest explanation is usually the best. Dark matter could be weakly interacting massive particles, actions, or primordial black holes, all of which fit existing frameworks without doubling the universe's particle content. Why invent mirror matter when alternatives require fewer assumptions? Some physicists argue that invoking a mirror sector is like hearing hoofbeats and assuming zebras instead of horses. The Bullet Cluster's gravity maps, for instance, align neatly with conventional dark matter models. Why complicate things? Even mirror matter's proposed solutions have loopholes. Take neutron oscillation. While experiments have spotted anomalies in neutron lifetimes, none conclusively point to mirror transitions. Other explanations, like unaccounted for experimental errors or unknown decay pathways, could fill the gaps. Similarly, galaxy rotation curves might suggest mirror matter, but modified gravity theories like modified Newtonian dynamics can also explain them without invisible particles. The cosmic microwave background's fluctuations, they're statistically consistent with standard dark matter simulations. Without a smoking gun, mirror matter risks being a solution in search of a problem. The strongest criticism might be pragmatic. If mirror matter exists, how do we ever confirm it? Most experiments rely on particles interacting via known forces. But if mirror matter ignores those forces, what's left? Gravity alone is a notoriously blunt tool. Detecting a mirror planet's pull would require precision beyond current technology, and even then, the signal could blend with ordinary dark matter's effects. Some argue that until mirror theorists propose a definitive experiment, one that can't be explained any other way, the idea will remain in the realm of intriguing what-ifs. Yet mirror matter isn't without defenders. They counter that scientific history is littered with ideas once deemed untestable: neutrinos, black holes, even atoms before technology caught up. The fact that mirror matter neatly solves multiple puzzles, dark matter, the matter-antimatter imbalance, neutron anomalies, suggests it's more than just a patchwork fix. And while alternatives like WIMP have dominated dark matter searches for decades, they've come up empty-handed. Maybe the real zebras are the ones we've been refusing to see. The debate boils down to a clash of philosophies. Should we prioritize simplicity, even if it means leaving cosmic mysteries unsolved, or embrace complexity if it weaves those mysteries into a grander symmetry? For now, mirror matter remains a tantalizing outlier, a theory too elegant to ignore, too elusive to confirm. And that's the heart of science, not just answering questions, but deciding which ones are worth asking. The hunt for mirror matter is about to enter its most daring phase yet, with a new generation of experiments and technologies designed to probe the universe's hidden twin like never before. At the forefront are next-generation particle colliders, like the proposed Future Circular Collider at CERN. This behemoth, with a circumference of over 90 kilometers, would smash particles at energies 7 times higher than the Large Hadron Collider, enough to potentially create exotic states of matter we've only dreamed of. If mirror matter exists, these ultra-high-energy collisions might produce fleeting signatures, anomalous energy losses, or unexpected particle trajectories that betray the presence of particles slipping into the mirror realm. Even more tantalizing is the possibility of dedicated mirror detectors, instruments tuned to catch the subtlest gravitational disturbances or quantum vacuum fluctuations that ordinary sensors miss. Meanwhile, in deep underground labs, scientists are refining neutron oscillation experiments to unprecedented precision. Facilities like the European Spallation Source are developing ultra-cold neutron traps, where neutrons are suspended in magnetic fields and monitored for vanishing acts. If even a fraction of these neutrons transform into mirror neutrons, the statistical power of these experiments could finally confirm their existence. Other teams are exploring quantum interferometry, a technique that exploits the wave nature of particles to detect minuscule gravitational influences. A passing mirror particle, though invisible, would warp space-time ever so slightly, potentially leaving a detectable ripple in the quantum interference pattern. Space telescopes are joining the hunt too. The James Webb Space Telescope's successors, like the proposed Lynx X-ray Observatory or the Habitable Worlds Observatory, won't just peer at distant galaxies, they'll map the gravitational scaffolding of the cosmos in unprecedented detail. By analyzing how light bends around galaxy clusters or how cosmic voids evolve, astronomers could spot discrepancies that reveal the presence of mirror matter's invisible structures. Even more revolutionary are pulsar timing arrays, which use the ultra-regular flashes of neutron stars as cosmic metronomes. If mirror matter clumps drift through our galaxy, their gravity would subtly alter the arrival times of these pulses, creating patterns that could unveil the hidden mass threading the Milky Way. Then there's the quantum frontier. Advances in quantum sensors, devices so sensitive they can detect a single photon's worth of energy, might finally catch mirror matter's whisper-thin interactions. Imagine a supercooled crystal vibrating in a vacuum, its atoms perfectly still. If a mirror particle nudges it gravitationally, the crystal's infinitesimal shudder could be amplified and measured. Projects like Aeon in the UK and Magi's in the US are already prototyping such detectors, aiming to turn quantum weirdness into a mirror matter microscope. Perhaps the wildest ideas lie in astrophysics. Some theorists propose that mirror matter could be detected indirectly through its impact on black hole mergers. Future gravitational wave observatories like the space-based LISA mission might spot anomalies in collision signals, extra echoes, or frequency shifts that hint at mirror matter's gravitational fingerprints. Others suggest hunting for mirror supernova. If mirror stars exist, their explosive deaths would emit gravitational waves and possibly mirror neutrinos, which could seep into our universe as unexplained energy bursts in detectors like Ice Cube. The common thread in all these ventures, they're not just incremental improvements, they're paradigm shifts in how we search for the invisible. Where traditional methods hit walls, these experiments exploit gravity, quantum mechanics, and space-time itself as tools to pry open the mirror sector. And while failure is always a possibility, even null results would tighten the constraints, forcing physicists to rethink or refine the theory. What makes this era so thrilling is the sheer diversity of approaches. It's not one experiment betting everything on a single outcome. It's a coordinated assault from particle physics, astronomy, and quantum technology, each angle shedding light on the others. If mirror matter is real, the conspiring whispers of these disparate fields might finally amplify into a shout we can't ignore. And if not, the journey itself will leave us with sharper tools, deeper questions, and perhaps a humbler appreciation for how much the universe still hides in plain sight. Just when mirror matter seemed like a fringe idea, recent breakthroughs have thrust it back into the scientific spotlight, not through direct detection, but through a series of mathematical revelations and cosmic coincidences that are too compelling to ignore. One of the most electrifying developments comes from a 2023 paper in Physical Review Letters, where a team of theoretical physicists demonstrated that mirror matter could resolve one of quantum mechanics' most nagging headaches, the cosmological constant problem. The universe's expansion is accelerating far slower than quantum field theory predicts it should, a discrepancy of 120 orders of magnitude. The paper showed that if mirror matter exists, its gravitational back reaction could counteract quantum vacuum energy, effectively erasing the discrepancy by distributing it across two sectors. It's like a cosmic accounting trick where the ledger balances only when you include the invisible column. Equally provocative are new models from string theory, where mirror matter emerges not as an ad hoc fix but as an inevitable consequence of higher dimensional geometry. In certain string compactifications, our universe's particles could be stuck to a three-dimensional membrane, while mirror particles occupy a parallel brane just a tiny distance away in an extra dimension. This brane world scenario, detailed in a 2022 Journal of High Energy Physics study, elegantly explains why mirror particles interact so weakly with ours they're literally operating on a different plane of existence. The math reveals a startling possibility. The mirror sector might not just mirror our matter but could host its own version of forces and particles entirely foreign to us, like a shadow standard model with unexpected twists. Then there's the anomaly in neutron star cooling that's reigniting debates. Data from NICER telescope revealed that some neutron stars are shedding heat 10 times faster than traditional models allow. A 2024 preprint on RZIV proposed a radical solution. These stars might contain cores of mirror matter, acting as thermal superconductors that siphon heat into the mirror sector. The paper's simulations showed that even a 5% mirror matter admixture could explain the observations, with heat vanishing as mirror phonons vibrations in mirror crystal lattices carry energy beyond our detection. It's as if these stars have secret drain pipes funneling heat into a hidden reservoir. Perhaps the most unexpected support comes from cosmic ray experiments. The alpha magnetic spectrometer aboard the International Space Station has detected an overabundance of high-energy positrons with no clear astrophysical source. While dark matter annihilation is a popular explanation, A 2021 study in Physical Review D showed that collisions between ordinary and mirror cosmic rays could produce the same signal. When mirror protons smash into interstellar gas, they might generate mirror pions that decay invisibly, except for the positrons that occasionally leak across the mirror barrier. The data fits eerily well, suggesting we're seeing the fallout of a shadowy cosmic ray universe operating alongside our own. Even cosmology isn't immune to mirror matter's resurgence. The Hubble tension, the growing disagreement over how fast the universe is expanding, might find a resolution in mirror particles. A 2023 analysis in Nature Astronomy demonstrated that if mirror neutrinos existed, their extra energy density in the early universe would subtly alter the expansion rate, bridging the gap between conflicting measurements. The kicker, these mirror neutrinos wouldn't need any exotic properties. They'd just be right-handed versions of the ones we know, completing a symmetry the standard model lacks. What ties these breakthroughs together is their refusal to treat mirror matter as a mere curiosity. Instead, they reveal it as a versatile tool, capable of solving disparate problems without inventing new physics each time. Whether it's taming quantum infinities, stabilizing neutron stars, or harmonizing cosmic measurements, mirror matter is proving its worth not through direct sightings, but through the quiet elegance of its explanatory power. And that's the hallmark of a theory with legs. It doesn't just answer one question, it answers questions we hadn't even thought to connect. The implications are profound. If these models hold, mirror matter isn't just a passive bystander in our universe, it's an active participant, shaping everything from quantum fields to galactic structures. Future experiments won't just be hunting for phantom particles, they'll be testing whether reality itself is a duet, played in harmony between seen and unseen hands. And if the math keeps pointing this insistently toward the mirror, we might soon find that the most groundbreaking discovery isn't finding new particles, but realizing we've been sharing the stage all along. At the heart of modern physics lies a deceptively simple idea that the universe, at its core, adores symmetry. Not just the kind you see in snowflakes or butterfly wings, but deep, mathematical symmetries woven into the laws of nature themselves. One of the most profound is CPT symmetry, the principle that the cosmos should remain unchanged if you simultaneously flip a particle's charge c, mirror its spatial coordinates p, and reverse the flow of time t. It's like a cosmic reset button. Apply all three transformations together, and reality should snap back into perfect balance. This isn't just a theoretical curiosity. It's a cornerstone of quantum field theory backed by mountains of evidence. And here's where mirror matter steps in, not as an intruder, but as a missing puzzle piece that could make CPT symmetry even more elegant. Think of it like this. If you film a particle's behavior and play it backward while also flipping its charge and reflecting it in a mirror, the resulting movie should still obey physics rules. But our universe has a quirk. While CPT as a whole holds firm, individual pieces don't always play fair. We've known since the 1950s that parity P can be violated, as Qin-Sheng Wu's experiment showed. Charge conjugation C also fails alone, since antimatter behaves differently than matter. Yet when you combine all three, CPT balance is miraculously restored. Mirror matter offers a breathtaking explanation. What if the violations we see are illusions, artifacts of only observing half the picture? If a mirror sector exists with flipped parity, it could counterbalance our universe's asymmetries, making CPT symmetry absolute at a level we've yet to perceive. Let's break it down further. Take a left-handed electron, a particle spinning in a way that violates parity on its own. Now imagine its mirror twin, a right-handed mirror electron with opposite charge. Apply time reversal and the pair transforms in perfect sync, their combined behavior preserving CPT symmetry like two dancers compensating for each other's missteps. This isn't just poetic, it's mathematically airtight. In fact, some theories suggest that the mirror sector isn't optional, it's required to keep CPT intact. Without it, the universe's ledger might not actually balance. The implications ripple through time itself. One of quantum mechanics' deepest mysteries is the arrow of time, why entropy always increases, why we remember the past but not the future. CPT symmetry hints that time's flow might be more fluid than we think. If mirror matter exists, it could have its own arrow, a mirror time flowing in parallel or even opposite to ours. Picture a mirror clock ticking backward as ours moves forward, with CPT symmetry ensuring the grand sum remains zero. Wild as it sounds, this idea isn't pure speculation. Experiments with entangled particles have already shown that quantum correlations can defy classical notions of causality, acting as if time's direction is negotiable. Mirror matter could be the key to understanding why. Critics argue that invoking mirror matter to fix CPT is overkill, that known physics already accounts for it. But supporters counter that nature rarely does things halfway. Every major symmetry in physics, from gauge invariance to Lorentz symmetry, has tangible consequences. Why should CPT be different? The search for mirror matter is in essence a test of whether the universe's deepest symmetries are truly universal, or if we've been missing the reflection that completes them. As detectors grow more sensitive and theories more refined, we might soon glimpse the truth. Whether mirror matter is the silent guardian of CPT symmetry or just another beautiful idea that doesn't pan out, the quest itself reveals something profound, that the universe's secrets aren't just hidden in the unknown, but in the symmetries we've yet to fully appreciate. And if history is any guide, every time we've peeled back a layer of nature's design, we've found not chaos but order, more intricate, more balanced, and more breathtaking than we ever imagined. Discovering mirror matter wouldn't just rewrite physics textbooks, it would shatter our most fundamental assumptions about reality itself. Imagine waking up one day to learn that everything you've ever seen, touched, or studied is just half of existence, that an entire shadow universe has been silently coexisting with us since the dawn of time. The philosophical whiplash would be unparalleled. For centuries, humans have gazed at the stars and pondered whether we're alone in the cosmos. But mirror matter poses an even more unsettling question. What if we've never been alone? What if we've simply been unable to perceive the neighbors sharing our space-time? This revelation would force us to confront the limits of human perception, exposing the arrogance of assuming that what we can detect defines all there is. Science itself would undergo an existential reckoning. The scientific method is built on observation, experimentation, and repeatability, yet mirror matter, by its very nature, defies all three. How do you observe particles that don't interact with light? How do you experiment with forces that ignore your detectors? The discovery would demand a radical expansion of what science even means, pushing researchers to develop entirely new methodologies for studying the imperceptible. It's akin to trying to study sound with a microscope or color with a thermometer. The tools we've relied on for centuries might suddenly seem antiquated, even naive, in the face of a reality where the majority of matter operates by invisible rules. Religions and worldviews would face their own upheaval. Many creation myths and cosmologies describe dualities: light and dark, spirit and matter, seen and unseen. But mirror matter would literalize these concepts in ways no theology anticipated. Would mirror particles be seen as the divine breath some traditions describe, an omnipresent yet intangible force? Would they challenge the uniqueness of human consciousness, suggesting that souls, if they exist, might have mirror counterparts? The potential for spiritual and ethical dilemmas is staggering. If mirror life exists, does it have moral value? If we can't perceive it, do we have obligations toward it? These aren't just academic musings, they're questions that could redefine our sense of responsibility in the universe. Even our cultural narratives would transform. Art, literature, and music have long grappled with themes of duality, doppelgangers, parallel worlds, the uncanny. But mirror matter would flip these metaphors from fantasy into fact. Suddenly, the mirror universe tropes of Star Trek or Alice in Wonderland would seem less like whimsy and more like prophecy. Creativity itself might take new directions as artists and storytellers reckon with a cosmos where every person, every object, every moment has a hidden twin. The very concept of identity could evolve as we're forced to ask, if a mirror version of me exists, does that make me less unique or more? On a practical level, the discovery could trigger both unity and division. Global collaboration might surge as nations pool resources to study this shared cosmic mystery, much like the international effort behind the Large Hadron Collider. Yet it could also deepen ideological fractures, with some groups rejecting mirror matter as heresy or pseudoscience, while others weaponize it to fuel conspiracy theories. History shows that paradigm shifts like heliocentrism or quantum mechanics often meet fierce resistance before acceptance. Mirror matter's invisibility might make it even harder to swallow, turning it into the ultimate litmus test for trust in science. But perhaps the most profound implication is humility. Humanity has spent millennia mapping the cosmos, confident that what we see is what exists. Mirror matter would be a cosmic gut punch, a reminder that we're still beginners in understanding reality. It's not just about finding new particles, it's about realizing how much we've missed, how deeply our senses and instruments have deceived us. That humility could redefine our place in the universe, not as its central observers, but as fleeting participants in a vast, double-layered reality we're only beginning to glimpse. And that's the true weight of mirror matter. It's not just a theory about particles, it's a mirror held up to humanity itself, reflecting back all we don't know and all we have yet to discover. For all its mystery, mirror matter represents something rare in science. An idea so elegant it feels inevitable, yet so elusive it remains just beyond our grasp. It's the cosmic equivalent of hearing footsteps in an empty house, sensing a presence you can't quite see. From the ghostly tug of dark matter to the eerie gaps in neutron decay experiments, the universe keeps dropping hints that we're missing half the picture. And that's what makes this theory so thrilling. It's not just about invisible particles, it's about the possibility of an entire shadow cosmos, woven into the fabric of our own, obeying the same fundamental laws but forever out of reach. But let's be clear, mirror matter is still unproven. For every puzzle it solves, skeptics rightly demand harder evidence. The absence of definitive detection could mean we're on the verge of a breakthrough, or that nature has a different surprise in store. Maybe mirror matter will turn out to be dark matter's distant cousin. Maybe it's a red herring and the truth lies elsewhere. That's the beauty of frontier science. The answers aren't handed to us, they're wrestled from the universe one experiment at a time. What's undeniable is how this idea has reshaped our imagination. It's forced us to ask how much of reality is still hidden. Could entire galaxies, stars, even civilizations exist right beside us, separated not by distance but by something far stranger, a fundamental flip in nature's blueprint? The very thought stretches the limits of what we consider possible, and whether mirror matter is ultimately confirmed or debunked, it's already achieved something profound. It's reminded us that the universe is under no obligation to make sense to us. The deeper we dig, the weirder it gets. So where do we go from here? The hunt continues, in underground labs tracking vanishing neutrons, in telescopes mapping gravitational distortions, in colliders probing the tiniest cracks in the standard model. Each anomaly, each unexplained result is a potential clue, and you don't need a particle detector to join the adventure. Stay curious, follow the science as it unfolds. Because the moment we stop questioning, stop wondering if there's more to the story, is the moment we stop discovering. Who knows, the next big breakthrough might come tomorrow. A lab somewhere might finally catch a neutron mid-flip, or a telescope might spot a gravitational glitch that defies all other explanations. And if that happens, we won't just be adding a new particle to the charts. We'll be stepping through the looking glass into a universe twice as vast, twice as strange, and infinitely more fascinating than we ever dreamed. Until then, keep looking. The universe's greatest secrets aren't always hidden in the dark. Sometimes they're right in front of us, just mirrored.